So far, we have considered a situation in which circular motion is uniform, that is, the angular velocity and the speed are constant. We saw that the linear velocity is tangential to the circle, while the acceleration points toward the center. If the motion is non-uniform, not only the direction of the velocity, but also its module, the speed, is changing with time. This means that there is a second component for the acceleration, which is parallel to the velocity, that is, tangential to the curve. The total linear acceleration of the object will be the vector sum of the centripetal and the tangential acceleration. Similarly to the linear acceleration, which is defined as the derivative of the velocity or the second derivative of the linear displacement with respect to time, we can define the angular acceleration as the derivative of the angular velocity or the second derivative of the position angle with respect to time. It is measured in radians per second squared. The angular acceleration and the tangential acceleration are related as indicated by this equation. This relationship is analogous to the one between the angular velocity and the tangential speed. Let us now consider the special case in which the angular acceleration is constant. If we integrate the definition equation, we find this relation for the angular velocity. Integrating again, we find the equation for the position angle. Compare these two equations with the equations for constantly accelerated linear motion.